Today we're going to talk about sketching graphs of polynomials without the use of a calculator. So first of all, local extrema is plural for local maximum or local minimum, also called the turning points of the graph. How do you find the possible number of local extrema for a polynomial? You take the degree of the polynomial minus 1, and that gives you the possible number of local extrema on the graph, not necessarily what it's equal to, but again, the possibility of how many you could have. The X-Intercepts, to find the X-Intercepts or zeros/roots solutions of the equation of a function, you must remember to set your y equal to 0 and solve for x. And when you do this, you're going to want to use the factored form, just like we showed in the last lesson, because that helps you to find those solutions. The Y-intercept, you set x equal to 0 and solve for y. So something that is new is the multiplicity. So this says if c is a 0 of the function, then the multiplicity of c is the number of times that c is a 0 for the function. So given that x minus c to the k power equals 0, we say that c is a 0 of multiplicity k. So what does that mean? Let's go ahead and plug some numbers in using this example that we have to the right. So for this, we have x minus 4 and x minus 3. So x minus 4, if the power is not written, remember it's to the first power, and x minus 3 is to the fifth power. So for this, that means we have, of course, x minus 4, and then this would be x minus 3 5 times. So 1, 2, 3, 4, 5. And if we solve x minus 4 equals 0, we get x equals 4. And over here, if we solve x minus 3 equals 0, we get x equals 3. And it doesn't matter for this that it's to the fifth power because you can only write x equals 3 once. So that's where the multiplicity comes in hand. So that's what we were saying up here, given that x minus c to the k power, we say that c is a multiplicity of k. It just means how many times is it occurring in the equation. So as you can see, this x minus 3 occurs a multiple of 5 times. So it's a multiplicity of 5, and x equals 4 is just a multiplicity of 1 because it only occurs once. So x equals 4 is a multiplicity of 1, and x equals 3 we say is a multiplicity of 5 because that 0 occurs 5 times. So for this, it says if the 0 is a real number, then it will be an X-intercept. So that means that the x equals 4 and the x equals 3 would be X-intercepts on our graph, which we've talked about before. We know their solutions, roots, zeros all mean the same thing. If a 0 has an odd multiplicity, then the graph of the function will cross the x-axis at that number. If the 0 has an even multiplicity, then the graph of the function will bounce at that number. So that means it touches the x-axis and turns around. Think about a ball hitting the floor. If a ball hits the floor when it bounces, it's going to hit the floor and bounce back, right? So that would be considered a bounce. Like think about that as the x-axis. So over here, this x equals 4 has a multiplicity of 1, which is odd. And x equals 3 had a multiplicity of 5, which is also an odd multiplicity. So that means that both of these would cross the x-axis at those solutions at x equals 4 and x equals 3. Another way you can remember that is just using this if this helps you. Cross is an odd number of letters. Bounce is an even number of letters. So if that helps you to remember that bouncing is for even multiplicities and crossing is for odd multiplicities, whatever helps you out. So let's go ahead and it says use the graph picture to the right to answer the following questions. So for this, it says, what is the smallest possible degree of the polynomial? So for this, let's actually come back to that and let's actually go to what are the x-intercepts of the graph. So if I look at the x-intercepts, I can see it crosses this is the x-axis right here. So it crosses the x-axis at 1 and negative 1, 2, 3, 4. So x equals negative 4 and x equals 1. What is the y-intercept of the graph? So it crosses the y-axis, it looks like at 0, 4 right there. And then write a possible equation for the graph. Okay, so we'll come back to this. So notice that for our graph that we have right here, this again was x equals 1. And notice that at the graph, it is hitting the x-axis and bouncing. So because it is hitting and bouncing, that means this has to be an even multiplicity because of that bounce. So it bounces on the x-axis. So even multiplicity. That means in the equation, the times you see that 0 should be an even number of times. So how many times does it factor? Looking right here, this as at x equals negative 4. Notice it crosses through the x-axis. So cross the x-axis means it's an odd multiplicity or an odd multiple. So this is going to help us determine what is the smallest possible degree of the polynomial function. Because remember, your zeros kind of help you write the equation. So for this, if this is a cross as an odd, well, what's the smallest odd degree that we have? 1. And what's the smallest even? 2. So if I add these up, 1 plus 2, that gives me 3. So this would be a smallest possible degree is equal to 3. Now, does that make sense with our end behavior? So with our end behavior, if we look at this, notice that the left end's down and the right end's up. So that means this is a degree that is odd, and the leading coefficient would have to be positive because the left end's down and the right end's up. So it makes sense that this is a degree of 3 for the smallest. Now, does that mean it could be something bigger? Sure, it could be degree 5, degree 7, but we're asking for the smallest possible degree. And again, using your solutions or your x-intercepts helps. And then again, if it crosses, that means it's an odd power of multiplicity, and even when it bounces. And so we just did the smallest possible degrees for those multiplicities, which is 1 and 2. So write a possible equation for the graph. If I want to write a possible equation for the graph, we can go backwards from what we did yesterday. Yesterday we were given the standard form and we factored to find the solutions. Now we're going to go backwards. So first of all, we want to write out the zeros. So the zeros, or the x-intercepts, are x equals negative 4 and x equals 1. So if I want to set this equal to 0, well then what's the factor? Add the 4 to the other side. X plus 4 equals 0. X minus 1 equals 0. So that means that this is the factor x plus 4 and x minus 1 for these zeros, because if I solve them, I get negative 4 and 1. At negative 4, remember this is the odd multiplicity, and this one was the even multiplicity. So for this, we would get, just in general, y equals x plus 4. It has to be to an odd power, so we'll just say 1, which is fine. And x minus 1 quantity squared. So this is a possible equation that we have. Now, we can actually get a little bit more technical with this by figuring out a point. So let's go ahead and use a point on graph that is not a solution, so not an x-intercept, to find A. So if we want to find what this A is, we can use a point and on the graph, any point that you want to use as long as it's not an X-intercept. And so because of course then what do? You plug those values in for X and Y and solve. So let's go ahead and use the point. The easiest one would be the Y-intercept. So the Y-intercept is 0, 4, and again it's not an X-intercept, that's why we can do that. So we can plug this in for X and this in for Y and solve for A. So we get 4 is equal to A times X is 0 plus 4 and 0 minus 1 squared. So if we solve, we get 4 is equal to A times 4 negative 1 squared. Remember, when you square, negative becomes positive, it's just 1. So we have 4 equals 4A, because A times 4 is just 4A, divided by 4. And that means A value is equal to 1. So a more precise equation to fit this graph would be y equals 1 times x plus 4 times x minus 1 quantity squared. Doesn't always happen that you get 1, but in this case we did. So that would be our possible equation. Again, how did we find that? We used our x-intercepts, our solutions, and then given those, we wrote the factors. And then if we wanted to write this in standard form, we would actually have to FOIL and combine like terms, which we're going to not do for right now. Okay, so the next example, say find all the zeros and state the multiplicities, and if the graph touches or crosses the x-axis. So I'm going to use B for bounce, and remember that has an even number of letters, so it's in for even multiplicities. C for cross, so that has an odd number of letters, so odd multiplicity. So first thing you want to do is find the zeros of the functions, or again, the roots, which are the x-intercepts, all mean the same thing, solutions. So remember, we do that by setting each factor equal to 0 and solving. And we talked about the last time why we don't need to write the powers, because when you take the square root or cube root for this last one of 0, then you just get 0. So here we get x equals negative 3, x equals negative 1, and x is equal to 1. So let's go ahead and write those down. X equals negative 3, negative 1, and 1. What's the multiplicity? So you look at the powers for how many times does it occur. So x plus 3 has a power of 2, so that means we have x plus 3 times x plus 3, so that's multiplicity of 2. This one has just to the first power, so it only occurs once, multiplicity of 1. And this last one occurs 3 times. So even, we know bounces, odd is going to cross. So bounce, cross, cross. Now for this next part, the degree, so remember this is not in standard form. So to find the degree, we said we can add up the multiplicities or the powers. We talked about that the other day. So 2 plus 1 plus 3 is equal to 6. So the degree is 6, which of course is even. And the leading term, it's not asking for the leading coefficient, the leading term. So if I think about multiplying this all out, x times x times x times 3 more x's, remember you're just adding those up, and in front the coefficients are all 1, so the leading term would be 1x to the 6. And the reason we need that is because the end behavior, that means this is even, and the leading coefficient is 1, positive. So even positive, remember, means both ends are going to go up on our graph. So how do you find the y-intercept again? Remember, you plug 0 in for x and solve. So we're going to do that into our original equation. So when I solve, I get y equals 0 plus 3 squared, 0 plus 1 times 0 minus 1 cubed. So 3 squared gives me 9, and this would be times 1. Times negative 1 to the third power is negative 1. So that gives me negative 9. So the y-intercept is 0, negative 9. I know for the end behavior, as x approaches either positive or negative infinity, my ends of my graph are both going up because it's even positive for the degree and the leading coefficient, because remember, use that leading term to help you define the end behavior. Now we have enough information to go ahead and graph this without having to use our calculator. So on my graph, I know that I need my zeros first, so I'm just going to count by ones on here. So 1, 2, 3, 4, 5, 6, negative 2, -4, -6. And on my y-axis, my y-intercept was 0, -9. So I'm going to count 5 2's. So 2, 4, 6, 8, 10, -2, -4, -6, -8, -10. So this is my x and my y-axis here. And so in order to graph this, we have our roots or our zeros or our solutions, x-intercepts, again, all mean the same thing. So -3, -1, and at 1. So because the next thing we talk about a lot was the end behavior. So now we know the end behavior both ends up go up. So these are the ends of my graph from these roots. So we know that this end has to go up and this end also has to go up. So then what's happening in the middle of the graph, we use our multiplicities to help us. So for the multiplicities, we said that -3 bounces, cross, cross. So at x equals -3, bounce means it's going to hit that x-axis and bounce back in the same direction. And then it crosses through. We also know it's hitting the y-intercept at -9. We have to cross through that, and then this one crosses through. So I know I did my graph correct because it crossed here. And so for this, how do I know how high to make this part right here, which is a local maximum? It doesn't really matter. So if you were to have made it go all the way up here and down, because we're not using our calculator, I wouldn't mark that wrong, so it's just a guesstimate. So you could have, instead of making your graph look like that, if you wanted to have made it go like this and make it look a little more symmetrical, or however, that's fine. Another thing we didn't talk about, that something that is a multiplicity of 1 crosses through, is something that is linear. But think about this right here. If we have a degree 3, so if I have x cubed graph, remember we talked about the cubic function, it kind of makes a little squiggle, makes a little squiggle on the graph when we go through. It looked like this when we graphed it. So this, if you have anything above 1, it actually is going to make a squiggle. So it makes a little squiggle. It's hard to write small with this. So it makes a little squiggle on our graph. So instead of crossing straight through this, I'm actually going to erase this right here and kind of make it have a little slight cubic squiggle. So something like that. So if we were to graph this using our calculator to check, it might look similar to this. It probably won't look exact, but we could always check it with our calculator. So I went ahead and plugged that into my graphing calculator, y equals. And after you have it into your graphing calculator, y equals, of course, you can go ahead and hit zoom 6 as a standard window just to see first the standard window. So you can see it looks like both ends go up from here, we know, so it looks like I can't see that maximum. So it went a little bit higher on the actual graph, but again, we were just drawing a sketch of the graph without using our calculator. So if I change this maximum maybe to 20 and hit graph, still is a little bit higher. I'm going to go back to my window and I'm going to do -5 to 5. Oops, I did the X, not the Y. I meant to do the Y. There we go. That's going to be better. So if I do 20, so it's still a little bit higher. So go back to my window and let's maybe do -20 to 30. And so now we can see what our graph looks like. So this is the ends of our graph both going up because remember the degree was even and positive for the leading coefficient. Here's the bounce on the x-axis, cross here and cross. And again, because it was an x to the third power, or I should say a cubic factor, notice it has a little bit of a squiggle instead of going straight through like this 0 over here. So you can use your calculator to kind of check your work to make sure you're on the right track. But again, your graph might not look exactly like that because we didn't know exactly how high this was going up. So really this goes way higher than what we have right here. But again, we're just drawing a sketch. So why don't you go ahead and do this next one on your own. Pause the video. When you're done, you can unpause to check your work. So for this, we have x plus 4 equals 0, x plus 1 equals 0. So x is equal to negative 4, and x equals negative 1. Oops. And we don't have another root, so this doesn't need to be here. The multiplicity, so this is to the third, this is to the second. So that means 3 is going to cross, 2 is going to bounce. So the degree, we add those multiplicities. 3 plus 2 equals 5. The leading term, think about multiplying this out. So there's no coefficients in front of those x's. So this would be like x to the third times x squared. So when you multiply something with the same base, you add the exponents. So 1x to the fifth. So that means for the end behavior, this is odd, positive, because this is odd and this is a positive leading coefficient. So odd, positive, think about y equals x. The left end goes down and the right end goes up. How do you find the y-intercept? Plug 0 in for x. So y equals 0 plus 4 cubed times 0 plus 1 squared. So 4 to the third power is what we have right here, times 1 squared. And for this, when we multiply this all out, 4 to the third is 64 times 1, so we get 64. So 0, 64 for my y-intercept. So this is odd, positive, so negative infinity goes towards negative infinity, and positive infinity goes towards positive infinity. So now we're going to use this information to sketch our graph. So for my graphs, I just went by 1 on the x-axis, and on the y-axis, I went by tens because we have to go up to, remember, 64 for the y-intercept. So my x-intercepts were negative 4 and negative 1, and then we had a y-intercept of 64. And for this, we said this was odd positive, so that means this left end from this 0 is going to go down, and from this 0 it's going to go up, but it also has to cross through that y-intercept, so we're going to go like this. And then what happens in the middle? Again, use your multiplicity. So in the middle, remember we said that at negative 4, it's a cross. Since it's to the third power, think about a cubic function. It's going to make that squiggle. Then the next one is an even multiplicity, so it's going to bounce, hit the x-axis, and go back. So this one is going to make kind of a squiggle. So I'm going to go ahead and kind of make this look a little bit more cubic. So it makes a squiggle. Then it's going to go up this way somehow, hit here, and bounce back in the same direction. Because remember, think about a ball hitting the x-axis and bouncing in the same direction. So this, of course, we don't know how high that goes because we don't know for right now until we know calculus how to get that. But this is just a sketch of the graph. So if you were to plug this into your calculator, you should get something similar to this. Of course, you would have to change the window on your graph so that you were getting that y-intercept. All right, so let's go ahead and do another practice one. So go ahead and do 3 on your own. When you're done, you can unpause to check your work. So looking at question number 3. So for this one, here we have negative 2 in front. So if I set negative 2 equals 0, is that true? No. So negative 2, because there's no variable with it, it's not actually a solution to my graph. It's just going to help you find the lead term, so because it's a coefficient. Here we have x plus 3 equals 0, x minus 1 equals 0, and x minus 3 equals 0. So x equals negative 3, x equals 1, and x equals 3. So be careful to not include that coefficient in front that did not have an x with it, because I often see students will try to write x equals negative 2. It's not actually a solution. So this has a multiplicity of 2 because the power is 2, 3, and 2. So that means this is going to bounce. This one crosses and this one's bouncing. Because this is a 3, think about the cubic function, so it's going to make a squiggle, just like a cubic function. For this, the degree, add the multiplicities, 2 plus 3 plus 2. gives us 7. The leading term, if I were to think about multiplying this out, now I have that -2 in front. So -2 times the 1 times the 1 times the 1 gives me -2 for the leading term coefficient, and then x squared times x cubed times x squared. So think about x squared times x cubed times x squared. If I have something with the same base being multiplied, we add the exponent. So x to the 7th. And we talked about that when we revisited our rules and properties of exponents. So -2x to the 7th would be my lead term if I were to put this in standard form. So it just saves us time just to look at those lead terms being multiplied. The y-intercept, so y is equal to -2 times 0 plus 3 squared times 0 minus 1 cubed times 0 minus 3 squared. So this gives us -2 times 9 times -1 times 9, which is equal to 162, because we have -81 times -2. So the y-intercept is 0, 162. So the end behavior, the degree is 7, which is odd, and the leading coefficient is negative. So odd, negative, think about y equals -x. The left end goes up, and now the right end goes down. So as x approaches -infinity, your y values go towards +infinity, and as x approaches +infinity, your y values are going to go towards -infinity. So now let's go ahead and sketch the graph of this. So I decided to go by 25 on the y-axis, and on the x-axis, again, just going by ones. And so if I go ahead and put my x-intercepts or solutions or roots, we have -3, and then the next one was 1 and 3. Our y-intercept we said was 0, 1, 62, which is why I went so high on my y-axis. We know the end behavior we said was odd, negative, so that means that the graph over here is going to go down, and on this side it would have to go up. And then we said that at -3 it was a bounce, so that means it hits the x-axis and bounces back. Then, of course, to get to this one, we have to go through the y-axis first, so it's going to have to go through here. At x equals 1, it was 3 for the multiplicity, so that means it's going to cross through, making kind of like a cubic squiggle, so like that somehow. And then at x equals 3, it was a multiplicity of 2, so again, that means the graph has to come back to the x-axis, it's going to hit it and bounce back down. So that makes sense that this part was going down because of our odd, negative, and then the even was the multiplicity for the bounce. So for the next one, go ahead and pause the video, do it on your own. When you're done, you can unpause to check. So for this one, 3 equals 0, x plus 1 equals 0, x plus 5 equals 0, and x minus 2 equals 0. 3 does not equal 0, so that's not a root, and again, it doesn't have a variable with it. So we get x equals -1 for this one, x equals -5, and x equals 2 when you solve these. The multiplicity is 3, 3, and this one would be 1. And so this is going to be a cross, cross, and cross. This one, because it's think about like a linear multiplicity to the first power, so that's going to go straight through. But these, of course, look cubic, so that's going to make a squiggle. So what happens if it's bigger than 3? Like maybe if it was odd and 5, I would just do a squiggle as well. The degree of this, again, add the multiplicity. So 3 plus 3 plus 1 gives us 7. The leading term, if we were to multiply this out, would be 3x to the 7th. So that means that this is odd power and positive leading coefficient. So the left end goes down, the right end goes up. Y-intercept, plug 0 in for x and solve. So 3 times 0 plus 1 cubed times 0 plus 5 cubed times 0 minus 2 to the first power. So when we do that, we get 3 times 1 times 125 times -2, which gives us -750. So 0, negative 750. So the end behavior we know is negative infinity goes to negative infinity because it's going down on the left, and positive infinity goes to positive infinity because it's going to up to the right. So I went by 100s on the y-axis and just again by 1s on the x-axis. So for this we have our roots at negative 1, negative 5, and 2. We said that this was odd positive, so the right end's going to go up and the left end's going to go down. We said our y-intercept was at 0, negative 750, which is why I made my y-axis scale so large. And then on the graph, we know that each of them cross through. So at negative 5, it was a degree 3, so it's going to make kind of a squiggle there. So I'm going to erase this and just kind of make it look a little bit cubic. So it kind of squiggles through. Same thing with that negative 1. So this has to come back over to the negative 1, squiggles through, goes to the y-intercept, and that's 2. It was to the first power for the multiplicity, so you can just make it look kind of straight as it goes through. So this is similar to what your graph may look like. Of course, if you were to make your graph here with the maximum go up higher, that would be fine. I wouldn't mark wrong where it was, or if you made it go down like this, that would be also fine. So there's different variations because we're not actually going to use calculus to find what that maximum or minimum value is. So that would be, again, a sketch of what our graph would look like. So we've just seen how we can graph polynomials using factored form. You can reverse the process and write the polynomial equation using the zeros to write the linear factors. So we have the factor theorem, which states that the expression x minus a is a linear factor of the polynomial if and only if the value of a is a zero of the related polynomial function. So we're going to write a polynomial function from its zeros. So each of these says write a polynomial function in standard form with the given zeros. So the first thing you want to do is write the factors. So this would be y is equal to negative 2 as a factor would be x plus 2. How do I know? Because if I set this equal to 0, I get x equals negative 2. So that's kind of how you can check. And then 0 would be x minus 0, and then x minus 3 with a multiplicity of 2. So x minus 0, we don't really need to write like that. We can just write that as x. So this would be y equals x times x plus 2 times x minus 3 squared. If I want to FOIL this out, then I would do the x minus 3 times x minus 3 first. So if I FOIL this, I get x squared minus 3x plus 9. So x squared minus 6x plus 9, and don't forget that's being multiplied by x plus 2 and also times the x. And so then I'm going to keep on foiling. So now I'm going to do this x times each of these terms here, and then the 2 times each of these terms. So we have x times x squared is x cubed minus minus 6x squared plus 9 x, and then plus 2x squared minus 12x and plus 18. So when we combine our like terms, we still have that x on the outside. This gives us x cubed minus 4x squared because we have our quadratic terms, and then our linear term here and here, so minus 3x plus 18, and then the last step would be to multiply by that x. So x times x cubed is x to the 4th minus 4x cubed minus 3x squared plus 18x. This would be the standard form of my equation given the zeros and the multiplicity that we had. For this one over here, we have y equals, this becomes x minus negative 4. This would be x minus negative 2 and x minus 1/3. So minus minus becomes plus, so x plus 4, x plus 2, And we don't like to leave this as a fraction because if you were to multiply that out with a fraction, it's going to be a lot harder. Think about when we did the slide divide, you can move that in front. So 3x minus 1, and you can even check 3x minus 1 equals 0. So 3x equals 1 when you subtract or add the 1 to the other side, divide by 3, and notice you get the 0 of 1/3. So you can always check your work. And if I did x plus 4 equals 0, so we subtract the 4 and get x equals -4. So you're just checking your zeros to make sure you wrote the factors correctly. So then, of course, the next step would be to FOIL these out. So it doesn't matter which ones or what order you go in. So here I have x squared plus 2x, and then plus 4x plus 8 times 3x minus 1. So this becomes x squared plus 6x plus 8 times 3x minus 1, and then we have to FOIL all this out. So take this x times these two, and same thing with each of the terms. So this gives me 3x cubed minus x squared plus 18x squared minus 6x plus 24x minus 8. And when I combine my like terms, I get 3x cubed plus 17x squared plus 18x minus 8. And that would be my standard form. So the next one says find any multiple zeros of the function, then write the end behavior of the function. So if I want to find the multiple zeros of the function, these are in standard form for number 1, and this should be say number 2, but it says 4. So these are in standard form, and number 5 is in factored form. So this one's the easiest. If we want to do this, that means in order to find the zeros, then we need factored form. So look for your greatest common factor first, which is x squared. So when we factor that out, we get x squared plus 6x plus 8. This is a trinomial. We know how to factor those. We look for factors of 8 that add up to 6. Both of these are positive. So of course that would be 4 and 2. 4 times 2 is 8, and 4 plus 2 is 6. So then now I have my factored form, and I want to find the zeros of this with the multiple zeros. So here we have x squared. So x squared equals 0, so x equals 0. X plus 4 equals 0, so x equals -4. And x plus 2 equals 0, so x equals -2. So the only multiplicity that we have is this square. These are both multiplicities of 1. So x equals 0 is a multiple of 2, x equals -4, and x equals -2 are multiples of 1, which isn't really a multiple, so just the x equals 0. For this, notice that in standard form, you look at the lead term. So this is the lead term here. So that is a degree 4, which is even. The leading coefficient is equal to 1, which is positive. So even positive means both ends go up. So as x approaches plus or minus infinity, your y values approach infinity. So go ahead for the next two, do those on your own. When you're done, you can unpause the video. So first for number 4, you want to look for the GCF, which is just x. And then you can factor this trinomial, x minus 2 times x minus 2. So that means we have x times x minus 2 squared. So that is the factored form. So here we have x equals 0, and for this one we get x equals 2. So with a multiplicity of 2 for that one. And the lead term, because it's in standard form, is x cubed. So this is degree 3, which is odd. The leading coefficient is 1, which is positive. So odd positive, think about y equals x. The left end goes down, the right end goes up. So you have to write this one separate. As x approaches negative infinity, your y values go down towards negative infinity. And as x approaches positive infinity, your y values go towards positive infinity. And this last one, we have, notice this is x plus 1 times x plus 1 squared. So really this is x minus 2 times x plus 1 cubed. So our zeros are x equals 2 and x equals -1 when you set these equal to 0 and solve. And so this one is a multiplicity of 3. And this is not in standard form, so you have to think about adding up your multiplicities. This would be a degree of 1 plus 3, which is 4, so even. And the leading coefficient, if we would multiply this out, would be 1, so even positive means both ends go up, so it's the same as the number 1. So as x approaches plus or minus infinity, your y values go towards infinity. And that is it for this lesson.